Article 430.32 of the National Electrical Code, or NEC, mandates the use of a separate overload device. This separation is specifically from both the motor itself and the motor's controller. The core reason for this requirement lies in the fundamental purpose of the overload device, which is to safeguard the motor against overheating. Overheating typically occurs as a consequence of excessive current being drawn by the motor. If the overload protection mechanism is integrated within the motor or the controller, its ability to accurately detect and effectively respond to overload conditions may be compromised. A variable speed drive, often referred to as a VSD, cannot be considered an adequate substitute for a dedicated, standalone overload device. The primary function of a variable speed drive is to regulate the rotational speed of the motor. It is not engineered nor intended to provide comprehensive protection against overload situations that could potentially damage the motor. Therefore, to ensure adequate protection, it is imperative to employ a standalone overload device. This device must be specifically rated to handle the full load current requirements of the motor in question. The overload device should be wired in series with the motor, and it should be physically positioned as close to the motor as is practically feasible. This proximity is important to ensure rapid and effective response to any detected overload condition. Now, let us delve deeper into the reasons why a variable speed drive cannot be relied upon for overload protection and examine the proper selection and installation of standalone overload devices. The variable speed drive's primary role is speed control, which means its internal current monitoring is geared towards maintaining the desired motor speed and torque, not necessarily preventing long-term overcurrent situations. While a VSD may have current-limiting functions, these are typically set to allow brief periods of high current, which might be necessary for acceleration or handling temporary load increases. These short-duration overcurrent events, while normal for motor operation under variable speed control, could still cause the motor to overheat if sustained for longer periods. The standalone overload device, on the other hand, is specifically designed to protect against these sustained overcurrent conditions. It does this by continuously monitoring the current flowing to the motor. If the current exceeds a predetermined level for a specified duration, the overload device will trip, interrupting the power supply to the motor and preventing potential damage. This tripping characteristic, defined by both the current level and the duration, is carefully selected based on the motor's thermal characteristics and its ability to withstand overloads for short periods without incurring damage. Now let us consider the different types of overload devices available. Firstly, there are thermal overload relays. These devices use a bimetallic strip or a melting alloy to sense the motor current. When the current exceeds the set point, the bimetallic strip bends or the alloy melts, causing the relay to trip. Thermal overload relays are relatively inexpensive and simple to install, but they are also susceptible to ambient temperature variations and may not provide the most accurate overload protection. Secondly, there are magnetic overload relays. These relays use an electromagnet to sense the motor current. When the current exceeds the set point, the electromagnet trips the relay. Magnetic overload relays are less susceptible to ambient temperature variations than thermal overload relays and can provide more accurate overload protection. However, they are typically more expensive. Thirdly, there are solid-state overload relays. These relays use electronic circuitry to sense the motor current. Solid-state overload relays offer the most accurate and reliable overload protection. They are also less susceptible to ambient temperature variations and can provide a wide range of protection features such as undercurrent protection, phase loss protection, and ground fault protection. However, they are typically the most expensive option. The selection of the appropriate overload device depends on several factors, including the motor size, the application, and the desired level of protection. For small motors and non-critical applications, a thermal overload relay may be sufficient. For larger motors or critical applications, a magnetic or solid-state overload relay may be more appropriate. Regardless of the type of overload device selected, it is crucial to ensure that it is properly sized for the motor. The overload device should be rated to trip at or slightly above the motor's full load current. The full load current is the current that the motor draws when operating at its rated horsepower and voltage. This information is typically found on the motor's nameplate. It is important to consult the NEC for specific requirements related to overload protection. Article 430 of the NEC provides detailed guidance on the selection, installation, and protection of motors. In addition to selecting the proper overload device, it is also important to ensure that it is properly installed. The overload device should be connected in series with the motor, and it should be located as close to the motor as possible. This will help to ensure that the overload device responds quickly and effectively to any detected overload condition. It is also important to ensure that the overload device is properly grounded. This will help to prevent electrical shock and ensure that the overload device operates properly. The installation should adhere strictly to the manufacturer's instructions and the requirements outlined in the NEC. Improper installation can render the overload protection ineffective or even create a safety hazard. Furthermore, regular inspection and testing of the overload device are recommended to ensure its continued functionality. Over time, components can degrade and settings can drift, potentially compromising the protection it provides. Testing involves verifying the tripping characteristics and ensuring that the device responds correctly to simulated overload conditions. Now let us consider a practical example. Suppose you have a 10 horsepower motor with a full load current of 28 amps operating at 460 volts. According to the NEC, you would need to select an overload device that is rated to trip at or slightly above 28 amps. You might choose a thermal overload relay with an adjustable range that includes 28 amps, or you could opt for magnetic or solid-state overload relay with a fixed trip point close to 28 amps. The specific choice would depend on the application and the desired level of protection. Once you have selected the overload device, you would need to install it in series with the motor, ensuring that it is located as close to the motor as possible. You would also need to ensure that the overload device is properly grounded. In summary, while variable speed drives offer advanced motor control capabilities, they should not be considered a substitute for dedicated overload protection. Article 430.32 of the NEC clearly mandates the use of separate overload devices to protect motors from overheating due to excessive current draw. Selecting the appropriate overload device, properly sizing it for the motor, and installing it correctly are crucial steps in ensuring reliable motor operation and preventing costly damage. Ignoring these requirements can lead to premature motor failure, equipment downtime, and potential safety hazards. Remember to always consult the NEC and the manufacturer's instructions for detailed guidance on motor protection. Consider the operating environment, the motor's duty cycle, and any specific application requirements when selecting and configuring the overload device. Regular inspection and testing will help to maintain the effectiveness of the overload protection system and ensure the longevity of the motor. Firstly, it is essential to understand the function of an overload device. Secondly, consider the limitations of variable speed drives in providing adequate overload protection. Thirdly, choose the appropriate type of overload device for your specific application. Fourthly, size the overload device correctly based on the motor's full load current. Fifthly, install the overload device in accordance with the NEC and the manufacturer's instructions. Sixthly, ensure proper grounding of the overload device. Seventhly, regularly inspect and test the overload device to verify its functionality. Eighthly, consult the NEC for specific requirements and guidance on motor protection. Ninthly, consider the operating environment and the motor's duty cycle when selecting and configuring the overload device. Tenthly, remember that proper motor protection is crucial for ensuring reliable operation and preventing costly damage. In addition to the points mentioned above, it is also important to consider the coordination of overload protection with other protective devices in the electrical system, such as circuit breakers and fuses. Coordination ensures that the overload device will trip before other protective devices, minimizing the impact of an overload condition on the rest of the system. Selective coordination is a key aspect of electrical system design, ensuring that only the affected portion of the system is energized in the event of a fault or overload. Overload protection is a critical aspect of motor control and electrical safety. Understanding the requirements of the NEC and properly implementing overload protection measures can significantly reduce the risk of motor failure, equipment downtime, and potential safety hazards. It is important to stay informed about the latest codes and standards and to consult with qualified electrical professionals when designing and installing motor control systems. Remember that proper motor protection is an investment in the long-term reliability and safety of your electrical equipment. The motor full load amps, or FLA, as listed on the motor nameplate, is the key value for sizing the overload protection. The overload relay setting must be based on this value, with the NEC specifying the maximum allowable percentage of the FLA for the overload trip setting. Exceeding these percentages can lead to nuisance tripping, while setting them too low can compromise the motor's ability to handle normal load variations. In many industrial settings, motors are subjected to harsh operating conditions such as high temperatures, humidity, and exposure to corrosive substances. These conditions can accelerate the degradation of motor insulation and increase the risk of overloads. It is important to consider these factors when selecting and installing overload protection. For example, a motor operating in a high-temperature environment may require a more sensitive overload relay to provide adequate protection. It is also important to consider the motor's starting current when selecting overload protection. Motors draw a significantly higher current during startup than during normal operation. This inrush current can cause nuisance tripping of the overload relay if it is not properly sized. Time delay overload relays are often used to accommodate the motor's starting current. These relays allow a brief period of overcurrent without tripping, giving the motor time to reach its operating speed. The selection of the appropriate time delay setting depends on the motor's starting characteristics and the load it is driving. The NEC provides guidance on the selection of time delay overload relays for different types of motors and applications. In addition to overload protection, motors also require protection against short circuits and ground faults. Short circuit protection is typically provided by circuit breakers or fuses. Ground fault protection is typically provided by ground fault circuit interrupters or ground fault relays. These protective devices must be properly coordinated with the overload protection to ensure that the motor is adequately protected against all types of electrical faults. Coordination studies are often performed to determine the optimal settings for the various protective devices in the electrical system. These studies take into account the characteristics of the motor, the electrical system, and the load being driven. The goal of coordination studies is to minimize the impact of electrical faults on the system and to ensure that only the affected portion of the system is de-energized. Another important consideration is the maintenance of motor protection systems. Overload relays, circuit breakers, and fuses should be regularly inspected and tested to ensure that they are functioning properly. The settings of protective devices should be periodically reviewed to ensure that they are still appropriate for the application. Proper maintenance of motor protection systems is essential for preventing motor failures and ensuring the safety of personnel and equipment. When troubleshooting motor problems, it is important to check the overload relay first. The overload relay is often the first line of defense against motor damage. If the overload relay has tripped, it indicates that the motor has been subjected to an overcurrent condition. The cause of the overcurrent condition should be investigated and corrected before resetting the overload relay. Common causes of motor overloads include excessive load, low voltage, and winding faults. If the cause of the overload cannot be identified, the motor should be inspected by a qualified electrician. The electrician can perform tests to determine if the motor is damaged and needs to be repaired or replaced. Replacing a motor can be expensive and time-consuming. Therefore, it is important to take steps to prevent motor failures. Proper motor protection is one of the most effective ways to prevent motor failures and ensure the long-term reliability of your electrical equipment. Let's examine a few scenarios to further illustrate the importance of proper overload protection. Firstly, consider a situation where a motor driving a pump experiences a sudden increase in load due to a blockage in the pipeline. Without proper overload protection, the motor would continue to draw excessive current, leading to overheating and potential winding damage. The separate overload device, properly sized and installed, would detect the overcurrent condition and trip, disconnecting the motor from the power supply and preventing catastrophic failure. Secondly, imagine a scenario where a motor operating in a dusty environment experiences a gradual buildup of dust on its windings. This dust acts as an insulator, preventing the motor from properly dissipating heat. As the motor temperature rises, the insulation deteriorates, increasing the risk of a short circuit. A sensitive overload relay, designed to detect even small increases in motor current, would trip before the insulation fails completely, preventing a costly motor replacement. Thirdly, consider a situation where a motor is subjected to frequent starts and stops. Each time the motor starts, it draws a high inrush current, placing stress on the motor windings. A time delay overload relay properly set to accommodate the inrush current would allow the motor to start without tripping while still providing protection against sustained overloads. These scenarios highlight the importance of selecting and configuring overload protection based on the specific operating conditions and application requirements. A one-size-fits-all approach to motor protection is not sufficient. It is essential to carefully consider all factors that can affect motor performance and to implement appropriate protection measures to prevent motor failures. Furthermore, the integration of advanced motor monitoring and protection systems is becoming increasingly common in modern industrial facilities. These systems use sensors to monitor various motor parameters such as current, voltage, temperature, and vibration. The data collected by these sensors is analyzed to detect potential problems before they lead to motor failures. These systems can provide early warning of overload conditions, allowing operators to take corrective action before the motor is damaged. They can also be used to optimize motor performance and reduce energy consumption. Advanced motor monitoring and protection systems represent a significant advancement in motor protection technology. They offer a proactive approach to motor maintenance, allowing operators to identify and address potential problems before they lead to costly downtime and repairs. Now, to address the specific question regarding the inspector's rejection of the variable speed drive as a standalone overload device, it is important to emphasize that the NEC is the authority on electrical safety. The inspector's interpretation of the code is based on years of experience and a thorough understanding of the principles of electrical protection. While variable speed drives may offer some degree of current limiting, they are not designed or certified to provide the same level of protection as a dedicated overload device. Relying solely on the variable speed drive for overload protection would be a violation of the NEC and could jeopardize the safety of personnel and equipment. It is always best to err on the side of caution and to follow the recommendations of qualified electrical professionals when designing and installing motor control systems. Remember that electrical safety is not just a matter of compliance, it is a matter of protecting lives and property. By implementing proper motor protection measures, you can significantly reduce the risk of electrical accidents and ensure the safe and reliable operation of your electrical equipment. Proper documentation of the overload protection system is also essential. This documentation should include the type of overload device used, the motor's full load current, the overload relay setting, and the date of installation. This documentation can be used to verify that the overload protection system is properly sized and configured. It can also be used to troubleshoot motor problems and to ensure that the overload protection system is properly maintained. The documentation should be kept in a safe and accessible location. It should be updated whenever changes are made to the overload protection system. Proper documentation is an important part of a comprehensive motor protection program. By following these guidelines, you can ensure that your motors are adequately protected against overloads and other electrical faults. This will help to prevent motor failures, reduce downtime, and improve the safety of your electrical system.